Chapter 2, The Chemical Bases of Life. For those of you that have already had chemistry, this should be an easy chapter. For those of you that have not had chemistry, this might require some dusting off of the cobwebs if you've had high school chemistry. So some of the big ideas of this chapter are on elements, atoms, and compounds, chemical bonds, and water, how water supports life. So in this presentation, we're going to just focus on the introduction of elements, atoms, and compounds. So life's chemistry is tied to water, and we'll discuss some of the important properties and what makes water so special later in this chapter. So life first evolved in water. We know that all living organisms require water, and that the chemical reactions in your body occur in cells consisting of 70 to 95% water. So organisms are composed or made up of elements in combinations we are going to call compounds. Living organisms are composed of matter. Matter is something that has mass and occupies space. We often refer to that as volume, so it has volume and mass. We do tend to use these two words, mass and weight. We kind of interchange those in science because, well, to be perfectly honest, mass has to do with how many, you could say how many atoms make up that object, where weight is actually a force. And that force is dependent upon gravity. So when we look at that, we know that if we were to take, or if, for instance, if you were to go and weigh yourself on the moon or even Mars, we know that because the force of gravity is less than what it is on Earth, you would have lost weight. Now, we know that that would not mean that we could wear that smaller size outfit that we've been trying to get into, because we didn't lose mass, we just lost weight, and that loss in weight is due to gravity, not because we shed off those unwanted pounds. But since we're not going to weigh things on Mars or on the moon, our gravitational factor, when we look at acceleration, which is 9.8 meters per second squared, is always going to be the same no matter where we weigh it on our planet. So that's why we tend to interchange them. But I do want you to know there is a difference between weight and mass. So to get back on track here, matter is composed of chemical elements, and an element is a substance that we can't break down into something smaller that is functional. We know we can break down elements into protons, neutrons, and electrons, but they don't retain those same properties as they do when they are together in a specific element. Now, there are 92 elements in nature, and only a few of them actually exist in a pure state. So in this picture, you can see the elements in the human body, and I always find this a little interesting because you can see that percentage of body weight. We've got a lot of oxygen, and then carbon's the next highest, and then hydrogen. So these four elements really make up most of the human body. And then we can almost call these like our trace elements. So we have these remainder elements that are only occupy or take up 3.7% of the human body. Now, what's a compound? So compound is a substance consisting of two or more different elements in a fixed ratio. For instance, water. You're always going to see water as H2O. All right, water is a compound. Carbon dioxide, we'll always see it as CO2. Right? So again, they're in a fixed ratio. So compounds are more common than pure elements. Sodium chloride, here's another one, here we go. Sodium chloride is a common compound with equal parts of sodium and chlorine. So in this picture, what they're showing you is that if we have sodium right here, which is a solid when it's pure state, and highly reactive, you put sodium in water and the temperature increases so high that it actually breaks down water and releases hydrogen gas, and the hydrogen gas can then ignite, so it kind of blows up. And then if you take chlorine, which is a gas at room temperature, a toxic gas that will kill you as well, and if you mix them together, it's just interesting that when you mix them together, they form sodium chloride, which is very harmless, and we put it on our fries and other food almost every day. So what we find is there are about 25 elements that are essential to life. 4 elements make up about 96% of this in weight, and we saw that in that previous picture. And those elements are oxygen, carbon, hydrogen, and nitrogen. And then we had mentioned the trace elements also in that last picture. Trace meaning that they're only needed in minute quantities, so very small amounts. So hopefully you'll take time to read these extra stories and tidbits they have in your book, because this kind of shows you how the information you're learning is connected to everyday experiences. And what we're seeing here is the structure here. If you look at this woman's throat, this is called a goiter. Now, we were talking about these trace elements and how we do see them in small amounts, but there are certain trace elements that we do need when we need iron in order to transport oxygen efficiently around your body. And in this particular case, this happens because of an iodine deficiency. So this is why today we have iodized salt. So we don't just have sodium chloride in those salt shakers. We also have potassium iodide, which is Ki, which gives us that iodine, which helps to prevent the structure called a goiter. So when we use our table salt, that iodized salt, it's helping to prevent this. Now, people are speculating with the new fad of eating sea salt that this might increase the amount of goiters that we see. Now, there are also trace elements are commonly used as additives to food and water. There are several chemicals that are added to help preserve it, to make it more nutritious and or make it look better. So you need to check out your the nutrition facts label on the food and drinks that you purchase. Now, this is a whole topic of debate that we could discuss in class, but there's a lot of things that we find in our food that are put in there to make it look or taste more appealing that may not be very healthy for us. But I'm not going to get off on my little soapbox on those types of things at this point in time. So atoms consist of protons, neutrons, and electrons. So each element consists of one kind of atom. And an atom is, again, the smallest unit of matter that still retains its property. It's not the smallest unit of life. The smallest unit of life is a cell. So, but the smallest unit of matter is an atom. So you should know the difference between those two. There are 3 subatomic particles in atoms, and they are that are relevant. We're not going to talk about what we could break down a subatomic particle into because we could go on and on and on. But we're going to talk about our protons, electrons, and neutrons. You need to know that protons are positively charged, electrons are negatively charged, and neutrons are neutral. They have no charge. So when we look at where these subatomic particles are located, we know that our protons and neutrons are packed into what we call the nucleus of the atom, which is different than the nucleus of a cell. And then the electrons are going to orbit. They're going to go around the nucleus. The negative charge of the electrons and the positive charge of the protons keep the electrons near the nucleus. So those protons and electrons are attracting one another, which keeps the electrons from flying off the atom. So you can see in this slide we have another formatting issue, but what they're trying to show you here is the element helium. So we have helium, and helium has 2 protons and 2 neutrons in the nucleus, and surrounding the nucleus in this electron cloud, we call this, are our 2 electrons that are going to be going around the nucleus. So again, we're not quite sure. There's not like a defined pathway around the nucleus. We just know that there's a good chance we'll find those electrons in about that area, which we're going to refer to as the orbit. So in order to find the atom's atomic number, and the atomic number refers to the number of protons, and we're going to practice this in class. And the mass number now, the substances that are actually making up most of the atom are the protons and the neutrons. Electrons have mass as well, or they wouldn't be considered matter, but they're so small that we really don't add them into the actual mass number of an element. So in order to get the mass number, we're going to add the number of protons and neutrons, which are approximately what we call 1 atomic mass unit. So here we have an atom of carbon, and I'm going to refer to this. So when we have our actual whiteboards, we're going to practice this next week, and I'm going to refer to this as our pen, P-E-N. And I'm going to ask you to tell me how many protons does carbon have, and you should be able to look at the periodic table and tell me, oh, it's got 6 protons. Well, if it's got 6 protons, which means it has 6 positive charges, then we're going to assume an atom is neutral unless we state otherwise. So we're going to assume then if we have 6 protons that we need 6 negative charges, that would be 6 electrons. Now, the mass number they're telling you here is 12, and we know for mass number, our mass number is the protons plus the neutrons. And since we have 6 protons, and we can set this up in an algebraic form, whoops, if I put the right numbers in. So we know 6 plus n equals 12, and if we were to solve for n, we would know that we have 6 neutrons. Just because we have the same number of protons, electron, neutron in this example does not always mean that they're going to be the same. We'll keep these 2 the same as long as we have a neutral atom, but that does not mean we'll have the same number of neutrons. So speaking of neutrons, so like we said, although all atoms of an element have the same atomic number, some differ in their mass number. This difference is referred to as an isotope. So different isotopes of an element have the same number of protons, because remember, if their protons change, we're going to change the mass number. Oops, sorry, not the mass number, the atomic number. Okay, we don't want to do that. Atomic number. Because if we have carbon, we want to keep carbon. But what's happening here is that we have a different number of neutrons. Because we have the different number of neutrons, the mass is going to end up changing. So you could think of an element that might be a little overweight or a little underweight, but it's still that same element. So the number of protons kind of distinguishes its characteristics. The neutrons may alter the weight of that particular element. Sometimes what happens is because they have those extra neutrons, it makes the nucleus unstable. And when it's unstable, it's going to try to get stable. And in order to do that, it has to give off energy. And sometimes it actually gives off some particles, some subatomic particles as well. And those are what we refer to as radioactive isotopes. So in this picture, we can see the different isotopes of carbon. So we have carbon-12, which is typically our normal carbon, you can say. When you look at the mass number of carbon, you see it's generally close to 12. But what we do when we put this nomenclature down, so we'll call this carbon-12, and 12 refers to the mass number. So if we have 6 protons, 6 neutrons, that gives us 12. Now over here we have carbon-13, which means we've got a heavier carbon. Now notice the number of protons does not change, but we know that these 2 numbers are going to need to add up to the mass, so we have an extra neutron. And then we have a third type of isotope of carbon, and that's carbon-14. And carbon-14, again, is going to have the same number of protons, or it will not be carbon. But because it's even heavier, yeah, we have to add that neutron. So we're up to two extra neutrons from our basic carbon here. Now, in order to get an element's mass number that you see on the periodic table, what they're going to do is they're going to take an average of all the isotopes. And then they calculate, that particular mass to put on the periodic table. So when we're talking about isotopes, there are some isotopes, again, that are not stable, and so we call them radioactive because they give off energy that can be harmful, especially if you're talking about like nuclear energy. That's all based off of using unstable isotopes they give off a large amount of energy. But the isotopes that we're using are like iodine, which are not dangerous. I mean, it's not like you'd want to use it every day, but most of us have had like a CAT scan or a special MRI that uses these radioactive isotopes. And what happens is you take them in, and usually it's an injection. In some cases, it might be a drink, and you give it time to go through the body, and then we can get some better pictures of what's going on, especially with soft tissue, than we would without using those radioactive tracers. So they are very helpful in the medical field. Again, it's not something we would use, over and over. Kind of like X-rays. X-rays are that's radiation as well, but there's definitely a certain number of X-rays that they'll only give you in a year because, again, if you get a lot of them, it could do tissue damage. So especially since many of you guys are going into the medical field, I would be sure to read that page 21, and it talks about how we use these radioactive isotopes as tracers and the type of instruments we use in order to see and get better pictures of what's going on with people when they are ill. So like I said, in addition to benefits, there are also dangers to using them. So again, if we use uncontrolled exposure, can lead to damage in some molecules, especially the DNA, which, again, when you damage DNA, then you have a higher chance of cancer. So we have chemical bonds, which we're going to learn about in this chapter. They're broken by that energy, and so that, again, all relates to cells not working properly. So again, just make sure you read page 21. So the rest of this chapter we'll finish in class. Be sure that you study for your quizzes. Remember, we'll have one on the class material we did last week and one on the lab material, basically scientific method. I would also just make sure you do your pre-class assignments, and you can always read ahead. And I'll see you on Saturday.